Hi everyone, welcome back. So in this session we're going to be talking about radical expressions in rational exponents. So first we have the principal nth root, which says that the principal nth root of b, which is denoted in this format, is the real number a so that a to the nth power equals b. For n even, the principal nth root of b is the positive real number a so that a to the nth power equals b, and if n is even, b must be non-negative, okay? So we call n the index of the roots, and b is called the radicand in this case. So those are just some general terms. So now let's get into some of the basic radical rules. So first we have a to the power of 2 squared is equal to a with the absolute value bars. So the absolute value bars basically just means that it's plus or minus a. I think most of you should be familiar with that. And then we have this, which is equal to a for n to be odd. And if n is even, then we're going to put absolute value bars around a. Okay, so it does matter if n is even or odd, because for even, you do need to put the absolute value bars. So just do not forget to do that. And then we have a raised to the power of n over n is equal to this, and it's also equal to that. Okay, so m is going to go inside of the square root, and the n is going to go on the left side. And you can write the m using the parentheses on the outside also. And then we have this rule, which allows you to basically separate what is multiplied inside of the square root into two separate numbers. So a times b should be equal to ab. And lastly, we have the division rule, which is kind of similar to the multiplication rule. It's provided that all roots are real, which I didn't mention before, but it's provided that all roots are real and that b is not equal to 0, because if b were 0, then this whole thing would automatically be undefined. Okay, so we can separate this into two smaller square roots, but still have the same n. So now we're going to look at a few examples. So first we have cube root negative 64. So the answer is negative 4. This should be pretty easy, because if you think about it, negative 4 times negative 4 times negative 4 gives you negative 64. So that's how you get negative 4. This one should be pretty self-explanatory. If we take a look at the second one, it just has an extra additional negative sign in front. So what we're going to do is we're going to separate this into negative 1 times cube root of negative 64. And from the previous problem, we know that cube root negative 64 is just negative 4. So we're going to multiply that by negative 1, and what you should get is a final result of 4. Okay? So now we're moving on. This one honestly should be easier than the other two. If you just think about it, 4 to the third power is 64, so you should just get 4. Okay? So when we take a look at the fourth one, this is actually not real, so no answer would exist for this problem, because we have an even root. So when we have an even root and a negative number inside the square root, it's always going to be not real. Okay, so if we have a negative number and the square root in this, then the nth root, which is this number here, has to be an odd number in order for a real number to exist. Otherwise, if it is an even power, then we say that it is not real. Okay, so moving on. So for this one, it's basically number 4, but we have an additional negative sign in the front. So we can simplify this into -1 times 4th root -16. So as we can see, since this, as we said before, does not exist, this whole thing does not exist, so we say that this is also not real. Okay? So moving on. So when we're looking at number 6, if you remember from the radical rules, a to the m over nth power is just nth root of a to the m. So if we look at this problem right here, since there is no parentheses around -64, we're going to treat them separately. So we can actually put a parentheses around this if we want to. So this is basically -1 times 64 to the 1/2 power. So we can rewrite this as the square root of 64 if we put a 1 and a 2 here, which are implied. Okay, so this is just 8, and don't forget to multiply this by -1, so we're going to get -8 as our final answer. Okay, so moving on. So this is basically just the same thing as that, but we have a parentheses, which means that it's going to be the square root of not 64, but the whole thing, which is -64. Okay, and since the nth root is even, because it's the square root, and this is, well, it doesn't matter if this is 1 or 2 or 3 or 4 or not, but since it is 2, we know that the expression does not represent a real number, and therefore it is not real. Okay, so like I said, whenever you see a even nth root and a negative number in the square root, it is always going to be not real. So moving on, we can rewrite this as the cube root of -64. So there is a implied 1 there, but we can disregard that. So we see that although this is a negative number inside the square root, we have a odd nth root. So this actually is not going to be not real. This actually represents a real number, and that real number is -4. Okay, so if you do -4 times -4 times -4, you actually get -64, so it makes sense. Okay, but for this one, you're not going to be able to get an answer if you think about it. Okay, so we're going to move on. So moving on to number 9, I already read out the explanations because this part of the video got cut off, but it's okay. So we have -8 to the -1/3, so now we have a negative exponent. So as we said before, we're going to regard the negative sign and this part as two separate things. So we're going to rewrite it as -1 times 8 to the -1/3 power. So the way that we get rid of this negative exponent is that we will take the inverse of this whole thing. So when I say take the inverse, we're just going to flip it upside down. So we're going to do 1 over 8 to the 1/3 power to get rid of the negative exponent sign. So that is just cube root of 8. So 1 over the cube root of 8 is just 1/2 multiplied by the -1, so we should get a final answer of -1/2. Okay, moving on. So since there is a parentheses around -16, we're going to treat this as a whole, but since we have a negative exponent, we have to get rid of that first. So we're going to do 1 over -16 square rooted, because 1/2 is just the square root. But that still doesn't erase the fact that it is going to result in a number that is not real, because we know that if the root is even and if we have a negative number inside of the square root, then it's going to be not real. So that's kind of messy. So as we can see here, we have a even root and a negative number. So whenever that happens, it is going to lead to a not real number. Okay, so moving on, we have negative 16 to the negative 1/2. First of all, we're going to separate these two. So we have negative 1 times 16 to the negative 1/2. So 16 to the negative 1/2 is just 1 over, first of all, and then 16 to the 1/2 is just square root of 16, which can be simplified to 1/4 times negative 1, which will give you negative 1/4 as the final answer. Okay, so we're going to skip 12 and move on to number 13. So for number 13, we have 1/4 to the power of negative 1/2. So in order to get rid of the negative sign, we are going to take the inverse of 1/4, which is actually just 4. So we're just flipping the denominator and numerator, okay? So what we end up with is 4 to the 1/2, which is just the square root of 4, so we get a final answer of 2. Okay, so last but not least, we have 25 over 16 to the 3 over 2. So we can rewrite this as the square root of 25 over 16 cubed. Okay, so after we recognize this radical rule, as you can see in radical rule number 4 above, we can simplify this to 5 over 4 to the third power, which is 125 over 64. Okay, so we're going to get rid of this first, so square root of 25 and then square root of 16, which gives us 5 and 4 respectively, and then we're going to do the cubed power last, because that is the easiest way to solve this problem. Okay? So now we're going to reduce the index of the root of each expression, and you may assume that all variables represent positive real numbers. So you might remember from last page where the radical rules talked about that a to the n over n power is equal to nth root of a to the n. So we're going to use that property for this. So we can actually rewrite this expression as x to the 3 over 6 power, and we can just simplify this exponent into x to the 1/2, and then we can convert this back to radical form, so this will just be square root of x. So if we do the same thing for this, we will write it as x to the 4 over 12th power and simplify it to x to the 1 over 3, and then finally cube root of x. So that's how you reduce the index of the root of an expression. So now we're going to talk about how to write expressions in their simplest radical forms. So an expression containing a radical is said to be in simplest radical form if all of the following are true. First, all exponents in the radicand must be less than the index. So what that means is that if you have cube root of, let's say, x to the 5th, for example, since this number is bigger than that number, we have to simplify this so that the exponent is less than the root. So, or the index, you can say. So what we can do is, according to radical rule number 2, if you look back on the front page, we can break this down into x to the 3rd times x squared, and then cube root the whole thing. Okay? So we can simplify this into this, so that 3 plus 2 equals 5. So these two are equal. And then after that, we can cancel the index root here, which is 3, with the 1 inside, and that is radical rule number 5. So we can cancel these. So what we get is x, and then we only have the x squared inside, and don't forget to write the 3 for the index root also. So now, since 2 is less than 3, all exponents in the radicand are less than the index. Okay? So the second rule says that any exponent in the radicand can have no factors in common with the index. That is pretty easy to understand. And then we have no fractions should appear under a radical, and no radicals appear in the denominator of a fraction, meaning that we have to rationalize all denominators. And we're going to talk about how to do this later. So let's look at a few examples. So first we have this. So first, what we're going to do is we're going to factor out 96. So we have 4 and 24, and then we have 4 and 6. So here we have 2 and 2, 2 and 2, and then 2 and 3. So we can say that 96 is equal to 2 to the 5th times 3. So we can actually rewrite this as 2 to the 4th times 2 to the 1st times 3. Okay? And if we plug this into this, we get, since these are two separate things, we're going to do 2 times, and then we have 2 to the 4th times 2 to the 1st times 3, and then to the 4th root. So from radical rule number 5, I think, you know that you can cancel these two, so we're going to take the 2 out. So we have 2 times 2, and then all the other ones are going to stay inside, and 2 times 3 is 6, and we're going to keep the 4th root. So if we combine the 2 times 2, we have 4, and then this as our final answer. Okay, so now we're going to look at the second one. So we're going to factor out the 250 to see if there is anything that we can take out, any factors that we can take out of the 250. So if we simplify 250, or factor 250, I should say, we have 2 times 5 to the 3rd. That's the factored form of 250. And so we can actually rewrite this as 5 to the 3rd times 2. Since the index and this are the same, we know that we can cancel these and take this out. So we have 5, and then cube root of 2. And then we look at this, we see that we can actually take the negative sign out of the radicand, because if you think about this, this is just 16 times negative 1 cubed to the cubed root. So if we separate this, we can do cube root of 16 times cube root of negative 1, and cube root of negative 1 is just negative 1. So what we can do is we're going to minus 3 here, and then also multiply it by negative 1, and then cube root of 16. Okay? And if we factor out 16, 16 is just 2 to the 3rd. Or we can say, actually it's 2 to the 4th, or we can say 2 to the 3rd times 2 to the 1st. So we can actually simplify this into 2 to the 3rd times 2 to the 1st, cube rooted. So if we cancel these and take the 2 out, we have the first part, and then minus 3. So that part is what we got before, okay? And then for this part, we have, as we've said, we have 2 that's just taken out, and then we have square root of 2 inside. So if you simplify this whole thing, we have this gives us 6, the whole thing. So we can just add these, and what we get is 11 and cube root of 2 as our final answer. So let's do a few more examples. So we have this, which we can simplify the expressions in the radicand into x to the third times x to the third, because they combine to make x to the 6th power. And then we can simplify the y's into y to the third and y to the 2nd, okay? And the reason that we're simplifying it this way is so that because the index root is 3, we want to be able to cancel out as much of the things inside as possible, so we can move them to the outside. So we can cancel out all 3 of these because from the radical rule number 2, I think you should know that. Yeah, so what we have is x times y, and then we have cube root of y squared. So if you combine these, you should get x squared y, and then cube root of y squared as the final answer. Okay, so moving on. I don't know if you noticed this yet, but this question says that you may not assume variables represent positive real numbers. So what that means is that if you have nth root of a to the nth power, like this, if n is even, then you have to have absolute value bars around a. If n is odd, which is all the cases that we have encountered so far, so if you look at this one, the index root is odd, which is why we don't need to write any absolute value bars. So if n is odd, then the answer is just a. But if n is even, like in this case, where the index root is 2, which is implied, then you have to write absolute value bars in the final answer. So let's see how this plays out. So we can separate this into square root of 9 times square root of x to the 6th. If you look on the first page, it's radical rule number 5. Okay? So we can simplify this into 3, and for this part that involves variables, since you cannot assume that variables represent positive real numbers, meaning that they can also be negative numbers. So when we have this, when we simplify this into x to the 6 over 2, which should be radical rule number 4 on the previous page, then you should get 3 times x to the third, but you have to put absolute value bars around this variable because you cannot assume that variables represent positive real numbers. Okay, so what you should get as the final answer is 3 times x to the third power, but with absolute value bars around x to the third. And this only happens when the index root is even. So if it's odd, like in this case, then we don't need to write any absolute value bars around the variables. Now let's look at more examples. So for 22, we're given this expression, and we need to write each expression in simplest radical form, and we may not assume variables represent positive real numbers. So if you remember from last page, if the index root is odd, then there is no need to write absolute value bars around expressions, around variables. But if this is even, then we do need to do that. So since 3 is an odd number, then we don't need to worry about writing any absolute value bars. So first we're going to separate the thing under the radicand into 3 different groups. So we have the negative sign, so we're going to write -1. Okay, we're going to separate the negative sign from the rest of the expression, and then we're going to multiply it by 24, and then we're going to multiply it by x to the 7th power. Okay? And our goal is to try to get as many things out of this radicand as possible. So we're going to factor 24 to see if anything goes to the 3rd power, so we can cancel it out with the index root. So if we factor out 24, we have 2 and 12, and then 2 and 6, and then 2 and 3. So 24 is equal to 2 to the 3rd times 3. So we see that 2 to the 3rd is raised to a power of third, so it can be canceled out with this index root right here. And so we're going to rewrite this as -1 times 2 to the 3rd times 3, and then for x to the 7th, we can rewrite this as x to the 3rd times x to the 3rd times x. So if you add up the exponents, 3 plus 3 plus 1 is 7, so that's why these two are equal. Okay? That is a rule of the exponents that you should probably already know from Algebra 1. So if we simplify this, there's supposed to be a 3 here. So we can take this out. We can take these two out. We can also take the -1 out. Because remember, -1, cube root of -1 is just -1. So what we end up is that we have negative, and then 2, and then x to the 2nd power, because we have 2x that's going to be taken out. And then what we're left with inside the radicand is a 3 and an x. So this should be your final answer. So moving on to 23. So you should be familiar with the steps already. So we're going to first separate all of the variables and numbers under the radicand. So we're going to do 256 times x to the 7th times y to the 2nd, just so that it's clear what we need to do. So now we're going to factor out 256 to see if anything can be raised to the 5th power. So we have 2, 128, 264, 64 can be 232, 216, 28, 24, and then 212. Whew, okay, so 256 is actually just 2 raised to the power of 8. So what we're going to do is we're going to write 2 to the power of 8 times x to the 7th times y to the 2nd. So we can also write this as 2 to the power of 5, so these can cancel out, and then 2 to the power of 3, and then x to the power of 5, and then x squared, and then y to the power of 2. We don't change the y because this number, this exponent inside the radicand, is already smaller than the index root, so we don't need to do anything. Okay? So after we simplify this, it will just be 2, which we can take out. So we have 2, and then we have an x, and that's all we can take out. So what's left in the radicand is don't forget to write the index root also. We have 2 to the third, which is 8, and then we have x squared and y squared. So this is the final answer. So that is the end of our notes for today, and we will pick up where we left off tomorrow.